Hello, everybody. Can you hear me? Okay. The number is very low. Just wait a few minutes. Maybe people can. Thank you very much. I'm fine. How are you? I hope everything is fine for you too. Açıkçası benim de bir fikrim yok. Hibrit yani online olacak sınavınız. Your exam will be online. I think last week of this month is the exam week. Hmm, Bir fikrim yok açıkçası. Üniversiteden uzak olduğum için siz benden büyük ihtimalle daha çabuk öğrenirsiniz. Yüz yüze mi online mi olacağına dair. Thank you very much. I'm fine. How are you? I hope everything is fine. Okay. As I see, we will continue with online courses. Most probably there will not be any laboratory or FPGA courses. Okay, number is low, but we have to start. Just upload the presentation. Okay. Okay, you can see the presentation, right? Good afternoon, welcome everybody. Okay, just wait 2 more minutes and we will start. Maybe people came. Okay, is everybody ready? We will start, and please keep pencil and pen with you because maybe we will do some exercises and I will ask you some questions. Last week we learned the Carnot diagram. We learned that we do a lot of things with Carnot diagram, and we can simplify the expression, any expression or any logic circuits with using the Carnot diagram, and it's very important. But in Carnot diagram, there was a construct like that. There is a we can only use that for 6 variables. We cannot use more than 6, and if you have any circuits about the, I'm sorry. Sorry, there will be interrupt. So we need another method for 6 or more than 6 variable inputs. When a function of more than 6 variables has to be simplified, mapping techniques become increasingly difficult to employ, and alternative methods have to be considered because the mapping techniques must be very boring, or must be take a lot of time. You have to choose the alternative methods. You have to consider that one. A commonly used alternative is the Queen-McCluskey tabular method. This technique is tedious, time-consuming, and subject to error when performed by hand. However, these difficulties can be overcome by writing a program which allows the simplification process to be run on a computer. As I said, it must be take a time. This method must be can be difficult. It can be take a time, but when you start the coding in the computer, you will use this method a lot. These difficulties can be overcome by writing a program which allows the simplification process to be run on a computer. The method is based on the complementation theorem, which can be applied to the simplification process systematically. We will see that. We will see how it's work. So, let's see the contents in this lecture. We will see determination of prime implicants. We know what does that mean, prime implicants. And the prime implicants charts. We will learn how we draw the prime implicant charts. We will see another method, Patrick's method. And we will see simplification of incompletity. Also, we will learn that specified function. We will learn another functions. And we will see another object, NAND and NOR implementation. Actually, you know that gates, but we will learn about the multi-input gates. What happens if the multi-inputs will used? Okay, objectives. Our objectives are to find the prime implicants of the function by using Quine-McCluskey method. Define prime implicants and essential prime implicants. We will see the differences about those terms. We will learn about the prime implicants and essential prime implicants. We will see what is the differences between them. Given the prime implicants, find the essential prime implicants and a minimum sum of products. We will say that SOP. You will see sum of product, it means. Expression for the function using a prime implicant chart and using Patrick's method. And We will learn minimize and incompletely specified function using the Quine-McCluskey method. Okay, let's see that. Determination of prime impedance. As I said, prime impedance is the important terms. The mean terms are represented in binary notation and combined using. You know this one, right? If we get x parentheses y and not y, it means x, right? This part is 1, so x and 1 is equal x. The binary notation and its algebraic equation. Let's see that there is an example. A not B, C, D, or A not B, C, D equals A not B, C. When we consider this expression, when we think about that, there's a 1, 0, 1, 0. Right? 0 means not, 1 means exactly the same. Or 1, 0, 1, 1. What is the differences between these terms? The last bit, right? The D. There's a not D and there's a D. You can parenthesis A not B C. You can get this D plus not this, and you can get this expression. And we will use dash. Dash also important. When the same bit, we will use dash for the same bit. It means it is not important. You can use the 0 or you can use the 1 instead of D, but it is not changing the results. Okay. Let's see determination of prime implicants, and let's begin the Quine-McCluskey. So let's start the Quine-McCluskey method. In the first step, there's a function. This is an example function. This is an example. I give you, for example, I give you mean term 0, 1, 2, 5, 6, 7, 8, 9, 10, and 14. And ask you simplify this function by using Quine-McCluskey. In the first step in this method, the first step is to make a group. You will take all of numbers. What does the 0 means? 0 means 0, 0, 0, 0. That one, right? And 1, 2, and 8. Okay, there's a group 1, there's a group 2, and there's a group 3. What is the differences between groups? Can you say that? What is the differences between 0 and 1? Why we group these numbers like that? Why we make groups these numbers like that? Why we say 1 to 8 is group 1? It's close, but not right. Just see details. Just look at details. What is the differences between, for example, group 1 and group 2? Yep. Congratulations. Let me take a photo. Name Talha Ferah Mohammed Sadal. Okay. There is a number of 1. it is important things in the Queen Mac class key method. Exactly, it is the important for all of methods. Number of one. We will take the numbers there from the function and make them a group. We will use group 0. It means none 1 is in here. We will use group 1. That means there is only one in the expression. We will use group 2. There is 2 1 in the expression. We will use group 3. It means there's a 3 1 in the expression. Okay, we learn how we group the numbers. It was the first thing we should know. Take a inputs, take a min terms, and make them a group. Okay, so let's start step 2. In the step 2, you can hear me, right? Because I put a mask because there is a some clinic in here and I took a mask. Okay, we will find two terms can be combined if they differ in exactly one variable, and we must to compare to combine whenever possible. Okay, let's see that. We try to combine the numbers, but two terms can be combined if they differ in exactly one variable, like a gray code, right? It must be just one bit change. For example, let's see the group 0. Okay, there is a 0 0 0 and 0 4 0. You only combine with the next group or the previous group. You cannot combine the group 2, right? Because there is already 2 change. There is already 2 1 and 2 bit change. You cannot group them. So it means you can group 0 and 1 because there is only 1 bit change, right? 0 and 1, and you will say that 0 0 0 and use dash for the changing bit. We use dash instead of the changing bit. Okay, and you can use 0 and 2 also, right? 0 and 2, it means 0 0 dash 0 because this bit is changed, right? This bit is changed and we use dash for this bit. We also can write 0 and 8. It means dash 0 0 and 0, right? Okay, we do the first step. Which one we use? We use this one, we use this one, we use this one, and we use this one. Okay, let's see the another groups. We can combine the group 0 and group 1, and we can also combine the group 1 to group 0. When you see 1 and 5, there is only one bit change, right? It means 1 5, it means 0 dash 0 1, not dash because 1 is not changing. It's the same. We only use the change 1 dash, this one. And let's see 1 and 6. but we cannot combine 1 and 6, right? Because there is a 6-bit changing. It's change 1 to 0, 0 to 1, 0 to 1. There is a 6-bit change. Only 1 bit have to change. Let's see another one. Let's see 1, 9. There is the same and change. Only 1 bit change. We can say that. We can write here. The first bit is change 0, 0, 1, right? And let's see 10. When we see 10, there is also 3-bit change, right? We cannot group 1 and group 13 because there is a 2 change. There cannot be any 1 change bits because there is already 2 ones differences between them. You can only combine with the next group and the previous group because it must be online 1 bit change. The other groups, you cannot see any 1 bit change because if we see the 14, there is a 2 bits change, right? There's a 3-bit change exactly. There's also 4, all of these change, and there must be only 1 bit changing, like that, right? So let's see the 2. We can say that. Let's see the 2 parts. This one. You can combine with the next group, and let's see that. When we see 5, there is a 3 change, right? 0, 0, 1, 0, 1. 2 and 6, there is only 1 change. It means 0, 2 and 6 dash 1, 0, right? There is only 1 bit change. In 10, you say it's okay. Let me camera. Okay. When we look at the 9, there is also 3-bit change. When we look at the 10, there is only 1 change. Sorry. Dash 0, 1, 0. Okay. Let's see other one. You got the logic, right? You know the logic of these terms. First column, you combine the expression, combine the number with only 1 changing bit. When we see 0, 10 in here, and when we look at this 8, it's combined with 9, right? Because there's only 1 bit change, this one, and we use dash for bit change, and there's a 10 also. When you use the expression, please tick that. You will use this tick, okay? 10, and when we got in here, okay, you can talk. You can ask, is there any miss? Is there any, I couldn't see. Okay, let's continue. And there is also 5 in here. You can combine with 7 and there is no one in the 5 because we already combined 5 with 1, and there is also 6. You can combine the 6 with 7 because there is only 1 bit differences. This means 0 1 1 dash. This bit is difference. And also you can combine the 6 with 14 because only 1 bit is changing. This bit is changing, right? And we can use this one, dash 0 0 dash 1 1 0. And the last one is 10 combine 14. Is there anything you don't understand? Do you understand well this column? This is the first step for the chart. All clear, okay. Let's see the other column. We will try to combine these terms. Okay, we will do the same thing in the last column. We have this expression. Okay, I cannot. This expression, this groups, and this groups. We can combine only the next group, right? Okay, let's see that. Is there one change bit in 0 1 and 1 5? No. This bit is difference, this bit is difference. It means 2 bits is difference. It's not combined. Let's see other one. Is that combined with this one? No, there is also 2 differences. Is that combined with this one? Nope, there is also 2 differences. Is that combined with this one? Also no, there is 2 differences. Is that combined this one with this one? Yes, dash 0 0, and there is only one changing bit. So we can combine these two, right? We can combine it. We can say that there is a 0 1 8. Sorry about the writing. I know it's ugly, but I am writing with mouse. So let's see another dash, right? There's another changing bit, and we got dash 0 0 and dash. Yep, Mariam, it is true. Let's see 202. Can you say that which one can be combined with 02? There's a, you said 28, but in the 28 there's a 2 differences in here, dash and 0. You said 8 10. Yes, it's fit because only differences is here, right? We can write this. We can write this one because in 0 2 8 9 it is the differences, and tick is also important. As I say, you have to tick whatever you use, and just write a tick near him, near it. So let's see another one. 08. 08 can be combined with you say it 2 1, there is only one bit changing into 1, right? It is true. And you say 1 9, and only one change is 1 9. It is also true. Okay, let's write it 0 8 1 9. When you say that, there is a dash, there is a 0, there is a 0, there is a dash. When you write the other one, 2 10, there is a dash 0 dash 0. Okay. Do you feel something in here? This expression is just like this one, right? I said before that there is not such a thing. For example, AB and or AB. What is the result? There is no such a thing to AB, right? The result is AB. Yes, it is repeats itself, and you don't have to use this one and also this one like this. You cannot have to, you don't have to use those one. And there is another combine like 2 6 10 14. Okay, Hamza, congratulations. Hamza Asaf, okay. And there is also another one, but it's the same. You can see the numbers and you can say that they are same: 2 2 10 10 6 6 14 14. It means they are same. You don't have to use both of them. You only want to use one of them. Okay. And we got the first results. There is a one implicant you don't use for combine, and there is another, and there is another. You have to use them for results because you didn't use for the column 3 this 3 operator, and you have to use them for create a results. And there is also this one. There is a 1 2 3 4 5 6. You have 6 expressions to the results. For example, what is this mean? There is a B C D. This means B C, right? What is that means? Not B, not C. I say it because it is a 0, and this means C, not D, right? I hope you get the logic. And we have just 1 2 3 4 5 6 expression to write results. We have this one 1 5, right? 1 5 means not A. Let's see that. 1 5 means not A, not C and D. Not A, not C and D. You have 5, 7 and 6, 7. You have 5, 7 and 6, 7, and you have these expressions and this one, right? There is another steps. It is not done yet. You can simplify these terms with using consensus theorem. You know the consensus theorem. Also, there is a definition. We will see this definition details next. Given a function f of n variables, product terms, p is an implicance of f if for every combination of values of the n variables for which p equals 1, f is also equals 1. We will see what does it mean. We will see the other present and other slides. And there is another definition: a prime implicance of function f is a product term, implicance which no longer an implicance if any literal is deleted from it. Okay. As I said, you can simplify this function with algebraic way. You can use consensus theorem or you can use other theorems and you can get this simplest version. But in the Queen McCluskey method, there is another step. Let's see the another steps. You get this 6 expression, right? Result of this column, result of this table. You get this one, this one, this one, this and this 6 expression for the results. Think about you are doing the division and you take the remainder like that. And we calculate the binary numbers, we use the division and we take the remainder, right? Just consider it you doing just kind of remainder. You combine the numbers and you take the remainder. Which one is right? This 6 one. Okay, let's create a table for this. You have this one and this one. This one is 0. Let's put it x 1. Put it another x 8. Another x 9. And you also have this one 2, 8 and 9. You also have this one 2, 6, 10 and 14. You will do that for all of the expression and you get this table, right? And you get this table. So char layout. Top row lists mean term of the function. All prime implicants are listed on the left side. Place x into the chart according to the mean term. What that form the corresponding prime implicants. We do that. We did that. We create the table, right? We create the chart. It is not hard. It is very simple. So essential prime implicants. It is the important terms. We know the prime implicants. All of them is the prime implicants. All of x is the prime implicants. But there is the essential prime implicants. It means you have to use them. You cannot avoid them. You have to use directly of them. If a mean term is covered only by one prime implicance, that prime implicance is called essential prime implicance. Like this. Like this one. Like this one. They are unique, right? When you think about this row, this column, there's only one. That means you have to use this one and this one. When you get this results, the results have to use all of this row. 1, 0, 1, 2, 5, 6, 7, 8, 9, 10, and 20. The result has to include all of them. There must be any missing. There mustn't be any missing part. You have to use all of them. Okay, let's see that. When you use this expression and this expression, because you have to use them, because there is an essential prime impedance, it means you take 0, 1, 8, also you take 10, 6, and 2. Okay, let's see that. Okay, let's say it again. If a mean term is covered only by one prime impedance, mean term means 10, 9, 10, 14, 0, all of them, all of this number is the mean term, right? If the mean term is covered only one prime implicate, like that, in this mean term and this mean term has only one prime implicate. There is not other. So prime implicate is called essential prime implicate. That means these two are essential prime implicates, and you have to take them for a result. You have to take this expression for create a result, because there is no other way. You have to use all of mean term in your results. When you use not B and not C, that means let's see that when you use this impedance, that means you use 0 and 1, you use 8 and 9. Also, you have to use this one, right? Because there is only one impedance in here. So you also use true mean term, 6 mean term, and the 14. Which ones are missing? There is a 3 missing, right? So it means it is not done. It is not done yet because there is also 3 missing. If you want to use this one, not BD, if it's useful for us, because there is also this one and this one. Also, we already use 0 and 2. We already use 8. So it can be not useful. We only use it for 10. Let's see another one. If we use this one, we already use 1. Okay, we can use it for 5. When you take this one, it means you got this, you also got this. So the result is not B, not C, C, not D, and A, B, D. With those true, let's see again. With this expression, we use 0 and 1, we use 8 and 9. With this expression, we use 2, 6, also 10 and 14. With this expression, we use 5 and we use 7. All we need, the remaining is that one, because when we use these two, there is a remaining 5 and 7. Actually, you have to decide yourself. You have to look at the chart and you have to decide which of them are the simplest and which of them include all of the min term. How can I create the simplest function with using all of min term? Okay, you have to decide it. It is not the hard way, but you need solve some exercises. Okay, so there is a result. It means we have not B, not C, plus C, not D, and or not A, B, D. This is the answer. Okay. The prime implicant chart can be look hard, but it is not. Trust me, it is not the hard way. When you look the chart, you will see the simplest solution for the example. Okay. There is another way for the prime implicant charge. In this way, you have to cross out the row of the select essential prime, like this one, and this one essential prime, and you just cross them. And also this one. And we do this first step. The columns which correspond to min terms covered by selected prime implicant are also crossed out, and we do also this one. Select a prime implicant that covers the remaining columns. The prime implicant is not essential. This one and this one is essential prime implicants. You have to use them. And there is a reminder. Which one do you use? You can use this and this two expression, or you can use just one expression and includes all of them. This is the reminder, right? Like that. You cross all of the essential one and you take the remaining cover. Okay? It is another way for this. So we will say that we will look at this definition, right? There was a two definition in here. Let's see the definitions. The terms that have not been checked off are called prime implicant. You know that we got F from the first table and we got the first expression. So you can use the, like we said, you can use consensus theorem and you can take this solution like that. Also, there is a definition of prime implicants. The first definition is, given a function of f of n variables, a product of term p is an implicant of f if For every combination of values of the n variables for which p equals 1, f is also equal to 1. Every mean term of f is an implicant of f function. Any term followed by combining two or more mean terms is an implicance. Okay. If f is written a sum of products form, every product term is an implicance. Let's see an example. There's an expression in here, right? They say that it is equal not B, not C, or A and C. You can do that with algebra because you know that you can use the not B, not C parentheses, and you get not E and A, not A and or A, and you get 1, and you get not B and not C. This. Also, there is the same expression in here, and you can get A and C. If A, not B, not C is 1 in here, if it's 1, there is no importance, not important in this equation, right? Because there is a OR gates, and in the OR gates, if there is a 1 bit is 1, so the result is 1. Then f is 1. If AC is 1, then f is 1 also. Because of that, when you look at this expression, if A and C 1, B is not important, because if you take the B, it means this expression is 0, right? B is 0, it means this expression is 0, but this expression is 1 because it is a not B. If you take B1, so this expression is 1 and this expression is 0, it's 1, f is 1. So it means this expression and this expression are implicants. If BC is 1 but A equals 0, f equals 0. So BC is not an implicant of f. Okay, this is the simple logic. So let's see the expression again. We say that not A, not B, not C is the prime implicants. But it is an exception about A. Because if A, not A, is deleted, not B and not C is still an implicant of F. So you can use not B and not C for that. You don't need A like that. And also AC is the prime implicant, and this two term is the prime implicants. Each prime implicant of a function has a minimum number of literals that no more literals can be eliminated from it or by combining it with other terms. So let's see Cohen-Maccleskey procedure again. You can see QM procedure. Find all product terms implicants of a function. Combine non-prime implicants. Remaining terms are prime implicants, right? Like that. We took only remaining one, right? Remaining ones are prime implicants. Okay. Remaining terms are prime implicants. A minimum sum of product expression consists of the sum of sum. It means non-necessary all of the prime implicants of that function. We need to select minimum set of prime implicants. It is your decision. You have to decide the simplest expression for the results. If a sum of products expression contains a term which is not prime implicant, so sum of products cannot be minimum. Okay, there's another way for the prime implicant chart. There's another example. You have this minterm expression. Cyclic prime implicants 2 more x in the every column in char, and you get this group. You can make a group with this expression, with this example, and you can take this. There's a missing, right? There is a third column is missing. You don't have to use third column in this way. You only get this chart, prime implicant chart, and you can get this f function. If you look at the chart, if you use this 3 action, this one, also this one, and also this one, it means you'll use all of minterms, right? That's also simple. But there's another way. Again, starting with the other prime implicants that covers column 0, the result table like that. You can use minterm. We will show that the result is this. We will prove. We must prove that. How can we get these results? Let's see that. You have this chart, right? A technique for determining all minimum sum of product solution from the PI charts. There's the PI chart, prime implicant chart, right? And you can use minterms with combine. So that means you can combine P1 with P2 because there is only one bit change. Also, you can use 1 and 3. There is a 1, there is a 1, there is a 1 differences, only 1 differences. This is not like gray codes. You only think decimal, and you only get the neighbor code. You can say that P1 and P2 is neighbor because it has the zeros, and you can say P1 and P3 also neighbor because they have ones. So we can write this expression with 2 and 4, 3 and 5, 4 and 6. Let's see 4 and 6. You have 4 and 6, and there is a 6, the same one. There is also P5 and 6. Okay. There is also, as you say, 6, 7, 5, 7 is reminder. No, there is not reminder. There is not reminds. We just use this expression, use for input, to make this expression. We just use the neighborhood. Okay, and there is also some theorems you know from the first Boolean algebra class. X or y and x or z means x or y and z, right? There's a one simple law. You have to remind, as I said, you have to remind that law in your mind. So we can use this rule, right? We can use this law for example, for this 2. It means x, y, x, z. You can say that it means this P1, X, and YZ. P2, 3, right? You can simplify the expression with using this law, these rules. Okay, this is the ordinary distributive law, you know, from the first Boolean algebra lessons. And you do the multiplication, and also you can eliminate the redundancy with using this rules. You also know these rules, x and xy means x, because when you get x parentheses, you get 1 and y. So that means there is a 1 and there is OR gate, that means ons 1, and you get x. And with using these rules, you get this one. So what we said about the chart. Let's see the chart. What we said about this chart, implicant chart. We said that you have to use all of minterms, right? You choose a special expression, special minterms. They have to include all of minterms, right? Result have to cover all of minterms. It is the same for this. The results have to cover all of minterms. Like, and if you know these rules, you get two different solutions. This one and this one. When you get this one, P1, P4, P5, or you can get this one. In this way, you always choose the simplest one. You don't want to use four inputs situation. You always want to deal with the simplest one, right? And you know the means of P1, P4, P5 means, because P1 means not A, not B. P4 means this one, B, not C. And P5 means like that. You can use both of them. Okay, you can use this solution or you can use this solution. You only choose, you can choose one of them. It is not important. You can choose one of them just like a solution, just like a results, but you must choose the simple one. So we prove that this function is equal this. Also equal this one, but not important. You can use both of them. So there's an example. Consider the function f a b c d, mean term 0, 1, 2, 3, 5, 7, 8, 10, 12, 13, and 15. Please fulfill the second list. You know the rules, right? You have to take a groups, combine. You can only combine with next one or previous one. You can only combine with this, or this. Just start with 0. You can start with 0, combine 1, it means 0, 0, 0 dash. You can combine 0, 2, it means 0, 0 dash 0. You can combine 0, 8. This is the easiest one. That's why I'm doing this first. And do the rest. If you finish, just say it's done in the chatting line. If anybody is finished, just say done. I'm giving you 5 minutes for that. There's another 1, 3, 0, 0, 1, 0. Samet Shafi. Congratulations. Anas Mustafa. Okay. Well done. We will wait 2 more minutes. Okay. Okay, let's check the seconds list results. Is that true? You're writing your table. If all of them match, please write match in the chat line. Is there anybody, all of them is match? All of them is correct. Okay, Hamza match. Okay. Thank you, Anas Mustafa, for being Anas. Okay, I'm giving you another 5. Okay. 7 and 50. Let's see. There's a 7 and there's a 50. Only one bit is difference. The others are same. So you can write -111. It is near because this group is 0, this group is 1, 2, 3, and 4. There's 4 group. Yep, there's a mistake. Thank you very much, Mohammed Asif. It is not matching. This one. Also, it is just mistake about the 13. 13 means this one is 0. There is a mistake about 13. Okay, and there's a check. It is mistake in here. 13 means 1, 1, 0, 1, because in here 1, in here 2, in here 4, in here 8. You take this, it means 30. There is a mistake in the table. Okay, truth table. So this expression is true. No, it is not wrong. It is, it is my mistake. Because I misdirect you with doing this mistake. 2 and 14. 15. 2 and 15. There's a 4 changing. Okay, let's do the third list. And this one is 0. Sorry about that. Let's try to fulfill the third one. There is exactly a clue in here because I forget the ticks. You can see that I use this number. There is kind of clue for you. You already know the reminder ones. If you done the third list, Please write the done in chat line. We will do a lot of exercises before the exam week. So don't worry, is there any missing? Is there any misunderstand about the subjects or lessons? We will do a lot of exercises just before the week exam week. We will do exercises from the beginning. Yes, it will be online, most probably. Actually, you know the system better than me. If you have any assignment, any announcements, you will learn just after me. Okay, is there any done? The top list, come on. You can do that. There is a clue. Okay. Just giving one more minute. Yes, there is no homeworks just yet. I'm preparing one, but I don't know when I will be sent you. I will announce about that. Maybe there is no one. I don't know. Okay, let's see the third list. Cemile just in time. Is that correct? Is that matching with your third list? You know these rules, right? You can just raise this one. You can just raise this one. Also, you can just this one. You only have those four impression and those three. You have six impression, right? Let's do prime implicant charts, and I want to see the simplest solution. There is a prime implicant chart, and you can see the essential prime implicants. You know what does it mean. And please write the simplest solution. Your solution must include all of min terms. Your results must cover all of min terms. You can write the results in the chatting line. You know that you have to use not we, not the. Also, you have to use be and the. There is also two term. There's another clue. Which terms you want to use? Which term you would use for your circuits? Okay, let's see that there is not A and also not B. Let's see that you also use this one, also use this one, right? Also use this one. Nope, you don't use this one. Okay, just use this one. Let's try again. You have to use this. The empty. You have to use this. Really. So you got this. You got this. You got also this. You got this. You got this. Unit. This one. Unit. This one. And also unit. This one. Right? You can use not E, not B for this. And also you can use this one. Okay, we can say that. Let's try it again. You have to use the essential prime, not B, D. And also you have to use BD. That means use this, you get those, you get those from that, you get also those one from that. You only need this one, and you only need this two, right? Let's see that we use not a, there is a multiple solution. Don't worry, you can write the right one because there's a multiple solution in here. You can use a B, and also you can use A, C, D, or you can use A, B, not C instead of that. You can use both of them. Okay, so with this expression you have all of min term included. As I said, you can use this one instead of this one. It is not important. Both of them is correct. There is a multiple solution. Usually there is a multiple solution in the logic circuits, in the binary system, in the Boolean algebra, in the Carnot diagram. Usually there is a multiple solution. You just need to choose one. Okay, let's see quickly with NAND and NOR implementation because you already know that. There's an inverter gate, you know, that's the NOT gate. There is also AND gate with NAND and inverter. There is also OR gates with using inverters and NAND gates. Actually, we are interested in the multi-input gates. As you see, a multi-input OR gate, for example, works the same way as the two inputs one. When either of its n inputs has a value of 1, the output will be 1. So it has an output of 0 only when all outputs are 0. Only in this situation, result is 0. All of the other situation, result is 1. NOR gates is just reverse it, right? In the NOR gates, you have to say 1, 0, 0, 0, 0. Okay. And multi-AND gate again works like a normal AND gate. It has an output of 1 only when all inputs have value of 1. It must be, all of them must be 1 for the results is 1. The other situation results are 0. AND case, as you know. Okay. There is a XOR gates. The XOR gates is not is another story because when the normal XOR gates you just look the differences between inputs. If they different, that means 1. If they same, that means 0. This time the logic actually changes. In normal XOR gates, we say the output is 1 when the inputs differ in the normal XOR. But this time we say that the output is 1 only when the number of inputs with value of is odd. It means if there is a 2, 1, result is 0 because it's even. If there is a 3, 1, result is 1 because it is odd. If there is a 1, 1, it means also odd, it means 1. Okay? You get the logic, right? If there's a 2, 1, it is even, so the result is 0. Okay? For multiple inputs of XOR. And there is another examples about and XOR gates. You know the NAND gates, not and you can say. You can say not or, and you can draw circles like that. Okay, it is the finish of the lessons. I hope you got the Queen McCluskey method. I advise look at a lot of exercises, look at a lot of examples from books or from the internet. Okay, see you guys in the next week. Thank you very much for listening to me. Have a nice day. Take care, all of them, all of you. See you in the next week. See you guys.